everyone very, very much for joining us. I'm Dr. Elena Hyde from the Allan I Carswell Observatory. This is our inaugural, and of course that means full of bugs, York University TeleTube. This is our all telescopes all the time. We talk about all kinds of great things. Online astronomy and astrophysics will be presented to you by our students and staff. We are very, very excited to have a wonderful presentation today. And all of our live streams are in fact live. We will be broadcasting again from the observatory as soon as it opens. But for now, we have an amazing presentation by two of our students, Sana and Gagan. All right, Sana and Gagan, take it away.
Hi, everyone. I'm Gagan.
And I'm Sana.
And we're from the Allan I Carswell Observatory in Toronto, Ontario. Today, we'll be telling you a little about what we do here at the observatory, and we'll stick around to answer your questions after the stream. The Allan I Carswell Observatory is located on campus at York University and is run by faculty, student staff, and volunteers. Outreach has always been a focal point of the observatory's operations, and due to the COVID-19 pandemic, we've decided to add to our online outreach programs with these live sessions on YouTube.
Our observatory consists of 2 domes, and each one of them houses a telescope. Currently, there's a 60-centimeter telescope and a new 1-meter telescope, which is the largest telescope on any Canadian university campus. Each of these are also equipped with a CCD camera, which is a very sensitive camera that we use for astronomical imaging. In addition to that, we also have a 40-centimeter telescope and many other smaller 20-centimeter telescopes. The reason all of them have names such as 1 meter or 60 centimeters is because they have primary mirrors that have diameters with those sizes. So a 1-meter telescope will have a primary mirror with a diameter of 1 meter. Most of our telescopes are reflecting telescopes, meaning they use mirrors to gather light. The amount of light they can gather depends on the size of the primary mirror. The bigger the mirror, the more light they're capable of collecting. So this makes the diameter of the primary mirror one of the most important features of a telescope. So that's what we use to name them. All of our telescopes get used for various things that Gagan and I will be discussing now.
So, outreach is a big part of what we do at the observatory. We're always trying to raise awareness and introduce more people to astronomy because what's not to like? As such, we try to make our observatory as open to the public as possible. Our major outreach programs include public viewings on Wednesday nights, when visitors can take a tour of the domes and the telescopes, and on clear nights, visitors have a chance to use the telescope. These times vary by season according to the sunset. Public viewings are temporarily being replaced by these live stream presentations and Q&A sessions, and our crew will be back with a new show weekly. We also host online public viewing sessions and broadcast a radio show called York Universe on astronomy.fm on Monday nights from 9 to 10 p.m. We also offer tours to groups who would like a closer look at the observatory, and these can be booked by email. You can reach us by email at observe@yorku.ca or visit us on Twitter, Instagram, and Facebook. Our social media, email, and website will be on the last slide for your reference. We also host a variety of other events with the observatory, such as star parties during Jupiter, Mars, and Saturn opposition periods, when the planets are closest to the Earth. We do star parties during eclipses, such as this picture on the bottom left is our event of the eclipse in 2016, I'm sorry. And we assist with outreach programs like Science Rendezvous every year to improve astronomy outreach. In 2019, the Royal Astronomical Society of Canada also hosted their annual General Assembly at York University, with observatory staff and volunteers running tours for attendees and assisting with other public outreach programs. Some of the cool things we like to do at bigger outreach events and tours include hands-on comet making and crater making workshops. We've also made interactive walkthrough constellation models that show how collections of stars appear from different positions in space.
Another thing that we do at the observatory is have students come up and use our telescopes to get some hands-on experience, which is a critical skill for astronomers. Every year, class has a project that students are assigned that involves the telescopes in one way or another. The first year project involves the moon. Students will come up to the observatory on a clear night and will view the moon through the 1-meter telescope at various magnifications while assisted by staff members. The moon is then imaged through our CCD camera, and these images are processed and sent to students. Some images taken during this year's first year project are shown on the slide. The first year students will then analyze these images to determine various things about the moon, such as to determine features such as craters, mountains, seas, and to find some landing sites of either manned or unmanned missions. The second year project consists of going up to the observatory at night in groups to get hands-on experience with collecting data with the 1-meter telescope. Students are not assisted by any observatory staff members, of course, unless they need help in this case. The focus of the second year project is the core of galaxies, specifically if a galaxy has an active galactic nuclei, or an AGN for short. All massive galaxies have a massive black hole at their core, which can either be active, in which case it has an AGN, or it can be inactive. An active galaxy, and thus an AGN, occurs when the black hole is consuming a lot of material. As material falls into the black hole, it moves at incredibly high speeds and it heats up from friction, and this causes it to emit a lot of light. So what students do is they take a series of images of a galaxy that's assigned to them by their professor, and then they analyze these images to determine how much light is coming from the core of the galaxy versus how much light is coming from the entire galaxy. If 10% or more of the light is coming from its core, then the galaxy has an AGN. The third year students will use the 60-centimeter telescope to observe an exoplanet transit. An exoplanet is short for extrasolar planet, which is a planet that orbits a star that isn't the sun. There are many ways to observe exoplanets, but at the observatory we use the transit method, which is illustrated in the bottom right of the slide. When an exoplanet passes in front of the star from our point of view, the planet will block some of the star's light, causing it to dim. As the planet continues in its orbit and moves away from in front of the star, it will return to its normal brightness. In this project, students will take a series of images of the star during the entirety of the transit, as well as for about half an hour before and after, and then they process these images to determine the brightness of star over the course of the transit. They use these measurements to generate a light curve that plots the brightness of the star as a function of time. The light curve will show how the star dims and then brightens again as the planet moves through its orbit, and is again illustrated in the bottom right image. The left image on this slide shows a light curve that was produced during this project when it ran last year. Students then use the information determined from the light curve to find out various properties about the planet, such as its orbital period, size, and its density. Finally, the fourth year project consists of using the 1-meter telescope to image an open star cluster. Open star clusters are groups of stars that form together and are thus gravitationally bound to each other. And they also have similar properties such as age and composition. An image of an open star cluster is shown on the bottom left of the slide. Students image an assigned cluster and then generate a color magnitude diagram, an example of which is shown on the bottom right. As you can see on the plot shown, a color magnitude diagram plots the magnitude of the star, which is a measure of its brightness, on the vertical axis, and then the color of the star, which determines its temperature, on the horizontal axis. The locations of stars on this color magnitude diagram will tell you at what point the star is in its lifetime. And when one is generated using all of the stars in a cluster, it will allow you to determine the age of the cluster.
Another big part of the observatory's operations is research. Most of the research we do here at the observatory is on variable stars. Variable stars, or more specifically, intrinsic variables, are stars at the end of their lifetimes that expand and contract, causing their brightness or luminosity to fluctuate on a periodic basis. We use our 60-centimeter telescope to conduct observations on different variable stars over the course of the year. We align the scope to the variable star and image it throughout the night and compare the brightness of the variable star to stable stars nearby in the field to observe how its luminosity changes. We use this data to construct a light curve like the ones shown on the top right of this slide for stars BE Lin and XX Sig. The star field on the bottom right is the field where XX Sig is located. This research can be useful in determining the distances of galaxies in and around the local group, and Edwin Hubble actually used variable stars to determine that the Milky Way was not the only galaxy in the universe, and that the Andromeda Nebula was actually our galactic neighbor. We also conduct research on stars with exoplanets, similar to the project that Senna mentioned earlier. The telescope, either the 1-meter or the 60-centimeter, images a chosen star over the course of the night and the brightness of the star is calculated over time. If the star has an orbiting exoplanet, the brightness temporarily decreases when the planet transits, seen as the visible dip in the light curve shown on the bottom left. In addition to exoplanet research and student projects we talked about earlier, we also use the 1 meter for observing in astrophotography. During tours or public viewings on clear nights, the crew on deck will select 5 to 7 of the most interesting objects in the sky to navigate the telescope to, and everyone visiting has a chance to view through the 1 meter. For example, when we have the telescope pointed at the Orion Nebula, the image at the top right is what the view through the eyepiece is like, which is pretty amazing. We also do lots of astrophotography using our CCD camera, which is essentially a really sensitive and powerful camera. We pick a celestial object to image and take a series of images in red, green, and blue CCD filters. These images are compiled to create a final image, and other edits are made to reduce background noise and enhance the quality of the image. The image on the bottom right is of the Eastern Veil Nebula, with the images taken and compiled by Sunna. Spectroscopy is something else new that we've been excited to add to our 1 meter program, as we are soon going to be installing a spectrograph. Astronomical spectroscopy can be used to determine physical properties of objects in space, such as chemical composition, temperature, and mass of a star. The 1 meter was installed on August 16, 2019. The dome the telescope was installed in was previously home to our 40 centimeter telescope, which was relocated to the Arboretum on campus prior to install. Since the 40 centimeter was so much smaller than the 1 meter, the platform and dome were both modified to accommodate the 1 meter. And the 1 meter was so big, in fact, that it couldn't be carried up to the dome the way the 40 centimeter was. It had to be craned in pieces and assembled in the dome. So on this slide, we have 2 pictures of the day of the 1 meter's installation. First light of the telescope was that same night. A crew from PlaneWave was on site to install the telescope and assist with first light operations so that everything would run smoothly. The Dumbbell Nebula picture on the left of the screen was one of the first images ever taken with the 1 meter telescope.
The 1 meter telescope is a reflecting telescope, so it uses mirrors to magnify light. There are many different kinds of designs for reflecting telescopes, and the optical design of the 1 meter is a corrected Dal-Kirkman, and a diagram of this is shown on the bottom left of the slide. The 1 meter has 3 mirrors: a concave primary mirror that is 1 meter in diameter, a convex secondary mirror, and a tertiary mirror, which are all labeled on the diagram. Light from an object will first strike the primary mirror and then get reflected to the secondary mirror, at which point it will be reflected again towards the tertiary mirror. From the tertiary mirror, the light will again be reflected into the instrument mounted on the 1 meter, such as an eyepiece or a CCD camera. Each step during this process further focuses the light and magnifies it. One of the many amazing features of the 1 meter telescope is its dual Naismith ports. Most telescopes only have 1 port, so only 1 instrument can be mounted at a time. But the 1 meter has 2 of them, so 2 instruments can be mounted simultaneously. The tertiary mirror is then capable of rotating between these 2 ports in just a few seconds. So for example, we can image an object with the CCD in 1 port, then flip the mirror over to the second port to take a look through the eyepiece. Doing this with the 1 meter is much easier than with telescopes with only 1 port, since we don't need to detach and reattach the camera to take a look at an object. All we need to do is press a button. How about how the telescope works mechanically? So how does it move and how does it point? There are many different ways of mounting a telescope, and the 1 meter is a kind of mount called alt-az, or altitude and azimuth. So it will move up and down in altitude and then rotate parallel to the ground in azimuth. A GIF of the 1 meter is shown on the slide. It's a bit of a sped up version of the 1 meter telescope doing a rotation. The dual Naismith ports on the 1 meter telescope are not its only unique feature. Most telescopes use gears to move. However, the 1 meter uses direct drive motors that are powered by neodymium magnets and coils, which allow for fast and nearly silent motion of the telescope. The motors are also very powerful, and when they're engaged, will ensure the telescope stays exactly where it is meant to be. The use of magnets also means that the telescope is magnetically levitating. While its motors will make it incredibly hard to move when they are engaged, when they are not engaged, the nearly 1-ton telescope is easily moved around by hand. Another unique characteristic of the 1 meter is how it points. In order to find and track objects, the telescope uses absolute encoders on each axis. An absolute encoder is essentially just a ring with many unique markings, so that a certain mark will always correspond to a given position. The 1 meter then has sensors that will read those markings on the encoders, which it uses to guide itself to the correct position. This means it has incredibly accurate tracking, and it also means we don't need to do nightly alignments, something that most telescopes do not allow for. With most telescopes, you'll have to turn on the telescope, find a bright star, point the telescope at it, and tell the telescope this is where you're looking. From there, it can go anywhere you want. But with the 1 meter, all the alignment we need to do is to create something called a pointing model every few months. What we do here is we take the telescope, we image the sky with it at around 80 to 100 different locations, and then it will run a program to determine the exact position of those images on the sky. This data is then saved, and the telescope uses this to guide itself and to track and point whenever we want for months to come. So this means when we want to use the telescope, it's incredibly simple. All we need to do is turn it on, connect the motors, and start pointing it to wherever we want to go.
Astrophotography is one of the most fun things to do with the 1 meter telescope. We use the CCD attached to a port on the telescope to take images of celestial objects, and we reduce these images using computer software. While the image reduction process is long, it is definitely rewarding when the end product is an image like these. A few months ago, just before social distancing went into effect, Sana and I actually spent a whole night up at the observatory doing a Messier marathon, where we tried to image each of the 110 Messier objects in a single night. We're in the process of reducing all those images now. The image on the left is Messier 15, a globular cluster in the constellation Pegasus, and the image on the right is a cluster of galaxies called NGC 7331, or more commonly known as the Dirichlet group. Here we have a few more images taken with the 1 meter telescope. To the left is Stephan's quintet, a group of 5 galaxies located close in the night sky to the Dirichlet group. On the bottom right is Messier 1, the Crab Nebula. The Crab Nebula is a supernova remnant nebula formed from the matter left behind by the explosion of a massive star at the end of its lifetime. On the top right is NGC 6503, known as the Lost in Space galaxy. It is a dwarf spiral galaxy located at the edge of the local group, which is the group of galaxies that the Milky Way is a part of. While astrophotography and in-observatory operations are currently on hold as we're all working from home, we have a lot more exciting stuff to share with you as we go forward with our live streams.
Well, everyone, you have been listening to the Allan I Carswell Observatory's TeleTube broadcast, the Astronomy and Astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Gagan and myself, Sana. You can always connect with us on Twitter at the handle @York Observatory, and check out our website for show notes, contents, update, and contact info at observatory.info.yorku.ca. Thank you for tuning in, clear skies, and have a good night.
Thank you, everyone. This concludes our first ever YouTube live stream from York TeleTube. Hope you all have had a wonderful evening. See you next week.